LHS 1140b, a potential new home for humanity? Introduction. LHS 1140b, a temperate exoplanet located approximately 39 light-years away in the constellation Cetus, presents a fascinating subject for astrobiological studies. As the second closest temperate transiting exoplanet known, LHS 1140b has emerged as a key focus in the search for extraterrestrial life due to its potential to host liquid water, an essential ingredient for life as we understand it. This report delves into the history, present understanding, and future prospects of LHS 1140b, exploring the compelling question: can we live on LHS 1140b? Historical context. Discovered in 2017, LHS 1140b is part of a planetary system that includes two additional exoplanets, LHS 1140c and LHS 1140d. The host star LHS 1140 is a low-mass red dwarf star with a mass about one-fifth that of the Sun and an estimated age of roughly 5 billion years. The discovery of LHS 1140b marked a significant milestone in exoplanet exploration, as it was one of the first temperate exoplanets identified in the habitable zone of its star. Initially classified as a mini-Neptune, subsequent studies using advanced observational techniques, particularly the James Webb Space Telescope JWST, have provided new insights into its composition and atmospheric characteristics. The shift in classification from mini-Neptune to super-Earth has sparked excitement within the scientific community, suggesting that LHS 1140b could have a nitrogen-rich atmosphere similar to Earth. Current understanding. Recent observations of LHS 1140b have provided compelling evidence for its potential habitability. Key findings include: 1. Atmosphere composition. The JWST observations indicate that LHS 1140b may possess a substantial atmosphere rich in nitrogen. This is a critical factor for the possibility of liquid water on its surface, as a stable atmosphere can help retain heat and maintain suitable temperatures. 2. Surface conditions. Studies suggest that LHS 1140b could either be an icy world completely covered in ice or a snowball planet with a liquid ocean beneath a cloudy atmosphere. The planet's surface temperature might reach around 20 degrees Celsius (68 degrees Fahrenheit), which is conducive to the existence of liquid water. 3. Potential for liquid water. LHS 1140b is situated in the habitable zone of its star, a region where temperatures may allow for liquid water to exist. Estimates indicate that the planet could have a vast ocean approximately 4,000 kilometers in diameter, making it one of the best candidates for confirming the presence of liquid water beyond our solar system. For radiation environment, the relatively low levels of ultraviolet radiation experienced by LHS 1140b compared to other exoplanets are advantageous for the potential emergence of life. This stability in the radiation environment could facilitate the development and maintenance of life-sustaining conditions. Future prospects. The future exploration of LHS 1140b holds significant promise. Key areas of focus include: 1. Further atmospheric studies. Continued observations with the JWST and other advanced telescopes will be essential for characterizing the planet's atmosphere in greater detail. Understanding the precise composition and dynamics of the atmosphere will be crucial for assessing its habitability. 2. Direct detection of liquid water. Future missions may aim to directly observe signs of liquid water on LHS 1140b. This would be a groundbreaking achievement in the search for extraterrestrial life, allowing scientists to confirm the planet's potential as a habitat. 3. Comparative planetology. LHS 1140b offers a unique opportunity to study a super-Earth in the habitable zone of a red dwarf star. By comparing its characteristics with those of similar exoplanets, researchers can gain insights into the diversity of planetary environments and their potential for habitability. For astrobiology and life detection, if LHS 1140b is confirmed to have liquid water, it will become an important target for astrobiological studies. Scientists will explore the possibility of life in its ocean and investigate the chemical processes that might support biological systems. Conclusion: LHS 1140b stands out as one of the most promising candidates in the quest for habitable exoplanets. With its potential nitrogen-rich atmosphere, suitable temperatures and location in the habitable zone, the planet presents a compelling case for the existence of liquid water and possibly life. As technology advances and our observational capabilities improve, LHS 1140b may soon provide crucial insights into the conditions necessary for life beyond Earth. The ongoing research into this intriguing exoplanet will undoubtedly shed light on the broader question of whether humanity might one day find a new home among the stars. LHS 1140b is a tantalizing exoplanet located in the constellation Cetus, approximately 39 light-years away from Earth. It is noteworthy for being the second closest known temperate transiting exoplanet orbiting a low-mass red dwarf star, LHS 1140, which is about 1/5 the mass of the Sun and has an age of approximately 5 billion years. LHS 1140b is classified as a super-Earth or potentially a mini-Neptune with a diameter around 1.7 times that of Earth and a mass approximately 5.6 times greater. The planet's atmospheric composition is of significant interest, with evidence suggesting it may possess a nitrogen-rich atmosphere, which is crucial for the potential habitability of the planet. The surface conditions on LHS 1140b remain under investigation, with hypotheses ranging from a completely ice-covered surface to a scenario featuring a liquid ocean beneath a cloudy atmosphere. The exoplanet lies within its star's habitable zone, which theoretically allows for the presence of liquid water, a critical ingredient for life as we understand it. Recent studies indicate that LHS 1140b may host a substantial ocean, potentially reaching up to 4,000 kilometers in diameter, with surface temperatures that could rise to a comfortable 20 degrees Celsius (68 degrees Fahrenheit). These characteristics make it a prime candidate for the search for extraterrestrial life. In 2024, observations from the James Webb Space Telescope JWST provided substantial insights into LHS 1140b's atmosphere, revealing that it likely contains a secondary atmosphere formed after the planet's initial formation. This discovery marked LHS 1140b as the first temperate exoplanet to display evidence of such an atmosphere, which is critical for considerations of its habitability. Moreover, the radiation environment around LHS 1140b is less hostile than that around many other exoplanets orbiting M-dwarfs, which often experience high levels of ultraviolet UV radiation that can inhibit the emergence of life. The lower UV radiation levels on LHS 1140b are considered beneficial for the potential development of life, as they may create a more stable environment for biochemical processes. One counterintuitive aspect of LHS 1140b's habitability is the notion that a snowball planet, characterized by extensive ice cover, could still support liquid water beneath its surface. The presence of a warm liquid ocean under a thick layer of ice could create conditions favorable for life, similar to what is hypothesized for some of the icy moons in our solar system, such as Europa. This challenges the assumption that a planet must exhibit clear signs of surface water to be considered habitable. Another surprising finding is the potential for abiotic processes to generate biosignatures. The unique high-energy radiation environment surrounding LHS 1140b could lead to the production of oxygen through chemical processes unrelated to biological activity. This complicates the interpretation of atmospheric data and necessitates a cautious approach when searching for signs of life, reinforcing the idea that we should not equate oxygen presence with life. Overall, LHS 1140b presents a unique opportunity to explore the possibilities of life beyond Earth, with its intriguing combination of atmospheric conditions, potential for liquid water, and comparatively gentle radiation environment. Further observations and studies will be crucial in determining whether this distant world can indeed support life as we know it. LHS 1140b is a fascinating exoplanet located in the constellation Cetus, approximately 39 light-years away from Earth. It stands out as one of the most promising candidates for habitability due to its potential for liquid water and a nitrogen-rich atmosphere. Here I will highlight some important content from recent studies and reports on LHS 1140b that many may overlook and explain their significance. 1. The nature of LHS 1140b, Super-Earth versus Mini-Neptune. One of the key aspects of LHS 1140b is its classification. Initially, there was uncertainty whether it was a mini-Neptune or a super-Earth. This distinction is critical because it influences our understanding of its composition and potential habitability. Recent observations using the James Webb Space Telescope JWST have strongly excluded the mini-Neptune classification, suggesting instead that LHS 1140b is a super-Earth with a nitrogen-rich atmosphere. This finding is significant because super-Earths are generally more likely to support life than mini-Neptunes, which tend to have thick atmospheres that may not be conducive to life as we know it. 2. Atmosphere and liquid water potential. The potential for LHS 1140b to support liquid water is another critical aspect often overlooked. Studies suggest that LHS 1140b may possess a vast substellar ocean with a diameter of approximately 4,000 kilometers. The surface temperature could hover around 20 degrees Celsius 68 degrees Fahrenheit, which is within the range conducive to liquid water. This finding is significant because the existence of liquid water is one of the primary indicators of potential life. Moreover, the presence of a nitrogen-rich atmosphere as indicated by the JWST data implies that LHS 1140b has retained a substantial atmosphere which could create conditions necessary for liquid water. This point is often overshadowed by discussions about the exoplanet's distance and size but is crucial for astrobiology. 3. Stable radiation environment. Another important aspect of LHS 1140b is its relatively stable radiation environment. Research has shown that the UV radiation levels on LHS 1140b are considerably lower than those experienced by Earth, which might facilitate the emergence and sustainability of life. This finding is significant because many exoplanets orbiting M dwarfs like LHS 1140 face high-energy radiation that can be detrimental to life. The stability of LHS 1140b's radiation environment suggests that it might be more hospitable than initially thought. 4. High FUV/NUV ratio. The FUV far ultraviolet to NUV near ultraviolet flux ratio on LHS 1140b is notably higher than what is observed on Earth. This high ratio has critical implications for the atmospheric chemistry of the planet. It suggests that abiotic processes could lead to the formation of oxygen, which complicates the search for biosignatures. In other words, while the presence of oxygen in the atmosphere could indicate life, it could also be produced through non-biological processes. This nuance is often overlooked in discussions about potential life on exoplanets. 5. Panspermia and interplanetary life transfer. The potential for life to transfer between planets and systems like LHS 1140 is a fascinating and often under-discussed concept. Given the close proximity of planets orbiting M dwarfs, the possibility of panspermia, where life might migrate from one planet to another, becomes a significant consideration. This point is critical for understanding the broader implications of habitability and the potential for life in the universe, as it suggests that life could arise on one planet and be transferred to another, increasing the chances of finding life beyond Earth. 6. Future research opportunities. The future research opportunities presented by LHS 1140b are substantial. As technology advances, particularly with the JWST and upcoming missions, scientists have the chance to conduct more detailed atmospheric studies. This could lead to direct evidence of liquid water biosignatures or even the detection of life itself. Many discussions focus on existing data, but the potential for future discoveries is what makes LHS 1140b a focal point in the search for extraterrestrial life. Conclusion: LHS 1140b presents a unique opportunity for scientists to study a potentially habitable world. Important details regarding its classification, atmospheric composition, stable radiation environment, and implications for life are often overshadowed by broader discussions about exoplanetary science. Understanding these nuances is crucial for advancing our knowledge about the universe and the potential for life beyond Earth. As research continues, LHS 1140b remains a prime candidate in the quest to answer the age-old question: are we alone in the universe? Key points for in-depth analysis and discussion on LHS 1140b. 1. Potential for habitability. LHS 1140b is positioned within the habitable zone of its host star, a low-mass red dwarf, which allows for the possibility of liquid water on its surface. The planet's estimated diameter 1.7 times that of Earth and mass 5.6 times that of Earth suggest it may be classified as a super-Earth or a mini-Neptune. Recent observations indicate that LHS 1140b might possess a nitrogen-rich atmosphere, which could play a critical role in maintaining surface conditions favorable for liquid water and supporting potential biological processes. This makes LHS 1140b one of the most promising candidates in the search for extraterrestrial life, as it may provide insight into the conditions required for habitability beyond our solar system. 2. Atmospheric composition and evolution. The analysis conducted with the James Webb Space Telescope JWST has provided initial evidence for a secondary atmosphere on LHS 1140b, likely formed after the planet's initial formation. This secondary atmosphere could include significant amounts of nitrogen, which is crucial for creating a stable climate that might support liquid water. Understanding the atmospheric composition is vital for assessing the planet's ability to retain heat and maintain conditions suitable for life. Further studies will need to confirm these findings and explore the implications for the planet's evolutionary history and potential biosignatures. 3. Radiation environment and its implications. The radiation environment on LHS 1140b, particularly the levels of ultraviolet UV radiation, is a critical factor in determining the planet's habitability. Studies suggest that LHS 1140b experiences relatively low UV radiation compared to other M-dwarf systems, which may be advantageous for the development of life. The stability of this UV flux is significant, as it can influence the chemistry of the atmosphere and the potential for abiogenesis. This aspect highlights the importance of understanding the stellar activity of LHS 1140's red dwarf and its impact on the habitability of surrounding planets. 4. Future exploration and research directions. LHS 1140b represents a key target for future astronomical research and exploration. The potential discovery of liquid water on its surface could mark a major milestone in the search for habitable exoplanets. Upcoming observational campaigns using advanced instruments like the JWST will be essential for characterizing the atmosphere and surface conditions of LHS 1140b in more detail. Researchers will need to focus on identifying biomarkers and understanding the planet's climate dynamics, which will provide valuable insights into the broader implications for life in the universe. These points collectively emphasize the significance of LHS 1140b in our ongoing quest to understand extraterrestrial habitability and the conditions that may support life beyond Earth. Each aspect opens avenues for further research, discussion, and exploration in astrobiology and planetary science. 1. The discovery of exoplanets. 1992, the first confirmed detection of exoplanets was made by astronomers Alexander Wolzin and Dale Frail, who found planets orbiting the pulsar PSR B1257+12. This landmark discovery opened the field of exoplanet research, leading to the realization that planets could exist outside our solar system. This case is significant as it marked the beginning of a new era in astronomy, transforming our understanding of the universe and the potential for habitable worlds like LHS 1140b. 2. The search for extraterrestrial life. SETI, the search for extraterrestrial intelligence SETI initiative began in the 1960s as scientists sought to detect signals from alien civilizations. The project has evolved over decades using advanced technology like radio telescopes and data analysis techniques. The ongoing search parallels the interest in LHS 1140b as both cases reflect humanity's quest to explore the cosmos for signs of life beyond Earth and assess the habitability of distant planets. 3. Mars exploration. The exploration of Mars, particularly through missions like the Mars rover programs, has provided significant insights into the planet's history, climate, and potential for past life. Just as scientists are investigating the habitability of LHS 1140b, Mars has been a focal point for understanding planetary environments and the conditions that might support life. The findings from Mars missions contribute to the broader context of astrobiology and the study of exoplanets like LHS 1140b. Future outlook: can we live on LHS 1140b? Overview of LHS 1140b. LHS 1140b is a temperate exoplanet located approximately 39 light-years away in the constellation Cetus. It is a super-Earth measuring about 1.7 times the diameter of Earth and possessing a mass roughly 5.6 times that of our planet. Recent research suggests that LHS 1140b may have a nitrogen-rich atmosphere and possibly an ocean under its icy surface, raising intriguing possibilities for habitability. Current understanding: LHS 1140b resides in the habitable zone of its host star, a low-mass red dwarf LHS 1140. Allowing for conditions that could support liquid water, an essential ingredient for life as we know it. Observations from the James Webb Space Telescope JWST indicate that this exoplanet might have a global ocean with a diameter of about 4,000 kilometers, with surface temperatures possibly reaching a comfortable 20 degrees Celsius (68 degrees Fahrenheit). The presence of a nitrogen-rich atmosphere could allow for a stable climate, further enhancing its potential for habitability. Future investigations. As we look to the future, the following predictions can be made regarding the habitability of LHS 1140b. 1. Enhanced observational techniques. The JWST and other advanced telescopes will continue to monitor LHS 1140b. Future observations will focus on characterizing its atmosphere more thoroughly and searching for biomarkers that indicate potential life. By 2030, astronomers anticipate a clearer understanding of the planet's atmospheric composition. 2. Astrobiological studies. Researchers will conduct astrobiological experiments to assess the potential for life on LHS 1140b. This includes experimental simulations of its environmental conditions to see if life can exist or emerge under such circumstances. By 2035, we may have preliminary results from laboratory studies that simulate the conditions on LHS 1140b. 3. Robotic missions. While human exploration of exoplanets is still far off, robotic missions to nearby celestial bodies such as Mars and the moons of Jupiter and Saturn could pave the way for future technology that might be adapted for missions to LHS 1140b. By 2040, advancements in propulsion and life support systems could make such missions feasible. 4. A public interest in funding. As the search for extraterrestrial life continues to capture public imagination, funding for astrobiological research is expected to grow. By 2028, we could see increased investments in missions that target promising exoplanets, including LHS 1140b. 5. Collaboration between scientific communities. The growing interest in exoplanet research will foster collaborations between various scientific disciplines, including astronomy, biology, and planetary science. By 2035, we may witness landmark interdisciplinary studies that combine insights from these fields to deepen our understanding of habitability criteria. 6. Potential for terraforming. If LHS 1140b proves to be habitable, discussions surrounding terraforming could gain traction by 2045. Theoretical models may be developed to explore how we could modify the planet's environment to support human life, though practical applications would remain speculative for the foreseeable future. Challenges and considerations. Despite the promising signs, several challenges remain. Distance and travel limitations. At 39 light-years away, LHS 1140b is beyond the reach of current space travel technology. Thus, our investigations will remain observational for the foreseeable future. Atmospheric stability. The long-term stability of LHS 1140b's atmosphere is still uncertain. Future studies will need to assess how robust the atmosphere is against stellar radiation and cosmic events. Biosignature detection. Distinguishing between abiotic and biotic sources of potential biosignatures in its atmosphere will be a significant challenge. Ongoing research in astrobiology will be critical to understand the implications of detected gases. Conclusion. The future of LHS 1140b as a candidate for habitability is exciting and ripe with potential. With continued advancements in technology and our understanding of exoplanetary atmospheres, we may eventually discover whether this distant world has the conditions necessary to support life. As we venture further into the cosmos, LHS 1140b stands out as a beacon of hope in our quest to answer one of humanity's most profound questions: are we alone in the universe?